Well said?
Well said.
Very good. Good morning to people in Durham, and good afternoon to those of you in Stockholm. I'm Earl Dow. I'm going to be your mentor, guide. I would prefer to avoid being your lecturer, but somehow I tend to get sucked into giving lectures. Even though I should tell you that there are some beautiful lectures that have been recorded over the last several years for this course. And therefore, you can just look at those. And I look younger in those lectures, but not too much younger. They're only the last year. So you're welcome to look at those. I think we have the homework brochures on the web as well. Of course, I change the homework each year. If I don't change the questions, I'll change the answers so that you'll be challenged or ask the questions in a slightly different way. We have a book. Since I'm one of the co-authors of the book, and actually I think it's wonderful, but it's not too bad. It keeps getting larger. This is the 5th edition. You could probably get a relatively inexpensive copy on Amazon or someplace like that. My assistant, Michelle Thompson, I think has some paperback copies, which are quite a bit less expensive than the hardback. As you may or may not know, it costs almost as much to produce a soft cover as a hardback, but the publisher charges you a lot more for hardback, thinking that the market will bear that price differential, which is probably true. Publishers of these kinds of books make their money by, first of all, selling it to libraries and covering all their costs. So any individual copies they get is pure profit. So don't feel badly if you get an inexpensive copy, but it's pure profit for the publisher anyway. Okay. Well, of all these chapters, we're only going to cover the first 4, and the first one is really just a few pages of introduction. And so we'll probably cover some other material that's not in the book, but might be in the next edition. So you might look for that. Let me begin by seeing if I can correctly pronounce your names. This is always a challenge for me, but you have to help me out. So I'm going to start with the folks here in Durham and then move to the folks in Stockholm. So let's see. I have to take my glasses off so I can read it. Yuhan Wang. You're not here. I mean, Danielle Vasily. How am I doing? Daniela. You pronounce the E on the end. Yeah. Daniela Vasily. I have a colleague in Israel. Her name is Daniela. She spells it differently. With the A on the end. Ravi, who's a very well-known aeroelasticity, and you may have occasion to look at her paper someday. Neil Mohan. How am I doing on that? Close enough. James Anthony. He's not here. He's not here. Ricky Hollenbach. Bach. Right? It's in Bach. As in the composer. Hollenbach. Jan Dreys. How's the last name? Is it Dreys? That's close? Oh, that's good. Sivanan Tavara Kanda. That's pretty good. That's not bad for the first time, right? Actually, much better than that. I'm above average. I had a colleague, we're working on hypersonic first structure interaction at NC State, and his name is Venkat Nani. I've got to pronounce his last name slowly in order to say it correctly, so I will try to pronounce your name slowly and correctly. David D. Nabila? Davide. Yeah. And Nabila? Nubila. The Nubila. Yeah. We'll have to work on that. Now, the last one is very easy. Boss. Your boss, right? Okay, I got the first name. How did I do the first name? Yeah, well, the last name is a little more challenging. It's Group Nibilek. No, Group Nibilek. How's that? Yeah, how do you say it? You've been practicing much longer than I have. So for the first time. Okay. Well, those of you in Stockholm, I'm not sure how many of you are there. I see a few faces in Stockholm. Hara Corvina. Is she there? You can wave at me if you're there. There's a 5-second time delay, so it takes them a while to hear me, which 5 seconds is forever. Okay.
It's not here today.
Not here today. Okay. Kamrul Lupak.
Also not here today.
Okay. Mohammed El Dayai. Antonio. Akshay Chalkin. Okay. Bart Suzanne Herzog. Matthias Takegi. I think Takegi. Yash Nigam. And Emmanuel Garcia. And a few of you are there. You're going to get extra credit for being there. Okay, I'll work on those from time to time when I hand back homework or other things. But at least that's a start. Let's see, logistics. I know you're here just for the learning experience and have no interest in grades or certificates or degrees or anything like that. But I will tell you about the grading system nevertheless. We'll have homework roughly once a week. Then at the end of the course, we'll have an oral final exam. How many people have had an oral exam before? Okay. How many people in Stockholm have taken an oral exam rather than a written exam in one of your courses? One. Well, those of you who have done it know that it's a wonderful experience, and those of you who have not yet done it will learn that it's a wonderful experience and will prepare you for the rest of your life, because once you graduate and no longer are a student, almost all exams in your life will have a second life. Occasionally, a lot of your exams. Okay. So that's what we're going to do. Then, what are we going to cover in the course? Oh, first of all, before I say that, thank all of you who turned it in for your first homework assignment. You may remember you told me your name, which I tried to pronounce, the name of your advisor, where you graduated from for your undergraduate degree, the research topic, and what you plan to do with the rest of your life. Although some of you fudged on the last question, I will not point out any individuals. But there are at least 4 students in the course, if they're still in the course, who did not turn in their first homework assignment. And I probably, for the first homework assignment, will not grade you less. But in subsequent assignments, it'd be nice if they were on time. So if you're one of the few people who has not turned in your first homework assignment, please do that. And soon, if not sooner, say by the time of the next class. And speaking of homework assignments, we already have a second homework assignment. And so let me write that down for you. It's important to keep our homework assignments going. The purpose of this homework assignment is to point out to you that you cannot believe everything you read in the book. Or in a lecture, for that matter. Hopefully, most of what you read in the book will be correct, and most of what you hear, at least in these lectures, will be correct. Occasionally, I might make a misstatement, and believe it or not, there's some typos in the book. So your next assignment is to find the typos. But I'm going to do it first. I'm going to tell you where to look. I made a note to myself. Homework assignment number 2. And homeworks are due a week from the day they're assigned. So this is due next Tuesday. So homework assignment number 2 is find the typos in the book. I'm sure you would have found them anyway, but maybe not. So I'll tell you what pages. I'm going to check the number they're on and how many there are. All the typos are in the equation because it's hybrid. That's compared to text. So on page 9, there are 2 typos. 10, there are 2 more. 11, there are 2 more. 13, there's 1. And 14, there's 2. If you read the rest of the chapter, on page 38, I discovered 1 too, although it's so obvious even I can find it.
A note for the class, we're going to be scanning these notes and uploading them to the Sakai page, which everyone should have access to, just so you're aware.
Thank you. By the way, you've just heard the voice of Michael Lee. Hello, Roy. Who is but I might even give him a chance to give a lecture because he hopes to become a faculty member, right? At some lucky university or something. Maybe that's true of some of the rest of you. Okay, so we've done the homework. Number 6, we have the name. Now let's talk a little bit. Well, let me pause for a moment. Any questions? Because now we're going to talk about aeroelasticity, having done the logistics for the course. Any questions? Stockholm, do you have any questions?
Yes, we have
They have an oral exam too. Do they have an oral exam?
My understanding is that those of you in Stockholm will only take the first half of the course. And therefore, the oral exam is at the end of the course. And therefore, I'm sorry to tell you that you will not be privileged to have the oral exam. But, at no extra charge, if you want an oral exam, I'm prepared to give you one by Skype. So if you like an oral exam, feel free to request it. I've offered that in the past, and I've not had too many people take advantage of the offer. Or if you'd just like to talk, we can do that too. So let's talk about the physical phenomena of interest. We're going to do 2 things in the course. One is we're going to talk about certain basic physical phenomena that occur in aeroelasticity. And sometimes people, rather than using the word aeroelasticity, they'll use a word like fluid structure interaction, because that's what we're talking about. We're talking about the interaction between the internal field and the deformation of the structure. That goes both ways, right? The forces deform the structure, but when the structure deforms, that changes the forces. There's a feedback loop. Anytime there's a feedback loop, you can take the course to control theory, you know there's a possibility of a dynamic or a static instability. So that's what we're talking about. And this occurs in aircraft almost from the very beginning. There was a peer and competitor of the Wright brothers named Samuel Langley, Dr. Samuel Langley. I think he was the head of the Smithsonian at the time, if I recall correctly, for those you know about that. And Langley Research Center, the NASA Research Center up in Hampton, Virginia, is named for Dr. Langley. And he built an airplane, which he hoped to fly. And he flew it off a plan for him. He wanted to, unlike the Wright brothers who flew over the sands of North Carolina, Dr. Langley flew over the waters of the Potomac River in Washington. Unfortunately, his plane had a structural failure, and that's why he was not the first person. The Wright brothers still had their chance. Well, it's said that it's likely, in retrospect, of course, they didn't know about these things at the time, they had an aeroelastic instability, he had a divergence instability, because his wing was not stiff enough. whether that's true or not, I think it's, no one's rebuilt his airplane and tested it, so we'll never know. But it sometimes does. The early days of the subject are largely driven by the technical needs of aerospace. But subsequently, people have realized that these same kinds of physical phenomena of interest to aerospace engineers also occur to civil engineers who build long span bridges, operate under the action of a wind, or a tall skyscraper, which can become very and vibrating. There have been a number of practical examples of that. If you look at the tongue, and there's an airflow of the tongue, and there's a condition for some people, unfortunately not too many, where there's actually a flutter of the tongue. There's a dynamic instability of the tongue, and that requires surgical treatment. What they do, they put something in to stiffen up the tongue. That's what we often do. Make flutter go away. There's blood flow through arteries, which is a fluid structure interaction problem. What else? Periscopes on submarines tend to have vibrations because they're tall, slender, flexible, and it's true they're not moving as fast as an airplane, but the density of the fluid is a lot bigger. It's all about the magnitude of the force, which goes roughly like the product of the density times the square of the flow velocity. Ships, hydrofoils can experience flutter. There's a literature on the flutter hydrofoil. So the heat elements in a new parameter can be fairly flexible. There's a fairly massive flow movement. They can become unstable and flat. And that's not a good thing. So lots of things can happen. But for the most part, since I'm an aerospace engineer, and that's really the historical origins of the subject, we'll talk about aerospace examples. The examples you like, if we bring them up. So, what are these physical phenomena of interest? There's something called divergence, which is a static instability. We'll probably start with that because it's traditional and interesting. There's something called control surface reversal. Which is also a static phenomena. It's not an instability, but it can be considered a static contact. If I have a wing and I have a control surface and I rotate the control surface, I do that for a purpose, namely to increase the lift. If I increase the force on the wing and the wing is flexible, then it can begin to twist. It turns out it twists in a direction such that it will reduce the lift. And sometimes the twist of the wing can offset the increased lift of the control surface, and there's a condition called reversal, where you actually get a net negative lift because the twist is so large. And that will happen at a certain flow velocity. It won't happen at a low flow velocity, but at a high flow velocity when the forces are larger, the twist will be larger, and therefore this can happen. So it's not an instability, but it's disconcerting because if I'm a pilot and I want to move the plane in one direction and I think I'm getting a lift in a certain direction, I get a lift component in the opposite direction. I have to think about that. Incidentally, one way that modern high-performance airplanes sometimes counteract it is they have a control surface on both the leading and trailing edge. And they each have a reversal velocity, but they're different, right? And so you can change through a control scheme. You can change the relative amount of control you're getting from leading trailing edge and fly beyond the nominal reversal velocity of any one control surface. That's an interesting thing to do. Okay, so we can do that. Those two things, statics. Then probably the physical phenomenon that allows aeroelasticians like myself to make a career out of it and get a reasonable salary each month is something called flutter. Flutter is a dynamic instability, which means that the structure interacting with the flow oscillates in time, right? And obviously a dynamic analysis or a dynamic model is a little more elaborate than the static model. In some sense, it's the dynamic counterpart of divergence. If you've flown an aircraft recently through a storm, you notice you bump around a little bit. That's usually considered an issue within the domain of aeroelasticity. In response to a gust, they call it gust analysis. So you're flying through atmospheric turbulence, you need to model the atmospheric turbulence, the forces that come from that, then compute how much of the structure is deforming or oscillating, find out whether that's excessive, either in terms of structural integrity or in terms of comfort of the passengers or the performance of the pilot. And so we need to do a gust analysis. So again, it's not it's dynamic. It's not an instability. And then finally, we'll touch on something called buffet, which is also a dynamic instability, but of a different sort than flutter, although it depends a little bit on how you categorize things. Even within flutter, as conventionally defined, it turns out there are 3 or 4 different kinds of flutter. And we'll discuss at least several of those. And I know quite a few of the people in this course are turbo machinery enthusiasts. Is that right? So one of the challenges in this area is to translate the language of turbo machinery into the language of airframes and vice versa. I'm more of an airframe person than Dr. Keel and Dr. Hall are more turbo machinery folks. So we can talk to each other. But when I talk about gust analysis, the turbo machinery people, I think, talk about inlet distortion or something like that. Because there can be a randomness in the flow coming into the inlet of the engine, and that's and that in turn can excite the blades and all that good stuff. And that's, broadly speaking, the counterpart of the entire aircraft flying through an atmospheric turbulence. Where now the motions are the motions of the entire airplane, rather than, say, individual blades or collections of blades inside the engine. But the mathematical models that people use are almost identical. Yeah. Not identical, but almost identical. The basic concepts, you would say. Okay. And of course, turbo machinery blades flutter, right? And they do. Buffet is another example where the language changes depending on whether you're an airframe person working for Airbus or turbo machinery person working for Siemens or someone. Buffet is used, well, often in the literature, people identify it as a physical phenomenon before they really understood it. But one thing you do when you encounter a threatening situation that's new is you give it a name, right? And that makes it a little less threatening. And so it's well known that aircraft, to talk about the aircraft issue for a moment, aircraft, if they fly too high and aims attack, the flow field can begin to oscillate violently, and that in turn causes the airplane to oscillate violently. So this usually occurs during maneuvers, but not all. There's a counterpart to that in turbo machinery. And in both cases, the flow field itself has become dynamically unstable. Even if the structure is really rigid and hardly moves at all, the flow itself can become dynamically unstable. That should not surprise you if you've taken a course in viscous flow, because probably the classical counterpart of that is I have a laminar flow, which is steady in time, right? It's flowing, but nothing is changing in time. But then there's a transition to turbulence. And turbulence is a chaotic or random-like oscillation of the flow. And then in between, there's something called transition. People are still doing research on. That's, and there's a boundary layer, right? And so the scales of importance typically scale on the order of the boundary layer. And there's a corresponding time scale that we'll learn about in this course. But in the case of Buffett, the flow probably is already turbulent next to the airfoil, right? It's already gone through transition from lambda to flow. But then there can be a subsequent instability on top of that classical instability. And that scale is on the order of the chord of the wing. So it's a much larger length scale, right, compared to the boundary layer thing. And the corresponding time scale is much different. So, Buffett is still a very hot topic in research. All these topics are still being worked on. Although, probably it's fair to say that as I go down this list, the research community is moving further and further down the list. And coming back to flutter for just a moment, there's a nonlinear counterpart to flutter called limbocycle oscillations. Turbo machinery can also exhibit limbocycle oscillation. And Buffett leads to a limbocycle oscillation. So much of the current research in the field is dealing with nonlinearity, and we'll touch on that. Having said that, I think that implies, and it didn't imply, I will tell it very quickly. If you go into history today, even today, almost all of the announcements done in support of the development of new aircraft or new engines is based on linear models. And so when someone encounters a nonlinear phenomenon like limbocycle oscillations, it wasn't intended, right? Nobody said, well, what are we going to do about that? And sometimes the answer is you learn to live with it, if the oscillations are not too large. But probably the design team didn't attempt to predict how large they would be. In fact, they hoped to avoid them altogether. But sometimes, despite the best efforts of some very competent people, experienced people, flutter happens and these other issues become important in a new aircraft design or a new engine design. Okay, so that's what we're going to talk about. And we're going to begin with divergent control system, control surface reversal. Last semester, if you look at the lectures from last semester, or last year, I didn't cover static aeroelasticity at all. Well, I've been doing this for a while. I have to make it interesting for me as well as for you, right? So I thought, well, they can read it. They can read chapter 2. And they had some questions on this file. So we did that, and we started with chapter 3, and then went on from there, talking about dynamics and aerodynamics and aerodynamics and parts of that. This time, I'm going to start off with divergence, in part because we have a guest from Brazil, Professor Bueno, and he's written a nice paper. He very kindly had me as a co-author on divergence, which is a classic. Except what he did is he added some nonlinear aspects to divergence. So that gives us a way to introduce nonlinearity into some of our models before we get into the complexity of dynamics. So we're going to do that. Are you still with me? Okay. Stockholm, are you still with me? That's good. That's the right answer. Thank you. Okay, so we're going to talk about divergence. And then after that, we'll talk about control system reversal. And we'll use the same control map models to do both. Well, let me start with this. We could try to model the entire airplane, right? But usually, that's not necessary. Usually, we just need to model the part of the airplane that's flexible enough that it will have a significant interaction with the flow. And so, often, in both wind tunnel models, as well as in mathematical models, we don't put the entire airplane there, or even a model of the entire airplane. We take a component, like a wing, or like the horizontal tail, or like the vertical tail, because from a fundamental point of view, they're all similar structures, right? And they have a flow past them, and they will all behave more or less in a similar fashion, fundamentally. So, a nice model would be, on it's a nice rectangular shape, but we could make it any shape we want. Shape isn't terribly important, but a rectangular shape is a nice place to get. So we would have a flow. Here's the wall of a wind tunnel, or if you like, it's a fuselage of an airplane. Here's the wing, or it could be a horizontal tail, or it could be a vertical tail if I want to kind of tail like that. And I like to ask what happens to this as we complete the flow block. Well, a number of different things can happen. But one thing that can happen, if I draw a dashed line, this is an axis, usually referred to as an elastic axis. About which that wing can flow. And it turns out that above a certain critical flow velocity, that cliff's going to become very large. In fact, if we use a linear model, remember those are the kinds that people usually use in science context? According to a linear theory, the critical velocity of the cliff becomes infinite. Doesn't really become infinite. A real large enough with the wind tunnel test, it exceeds the yield of the material and breaks the model. And it turns out the velocity, which is actually very close to that predicted by the linear theory, is saying there's going to be an infinite twist. And so that linear model is used to identify what flow velocity beyond which I probably try to do the wind tunnel test or apply the airplane. On the other hand, if it turns out that there's a linearity in the system, as we discovered, if I have a nonlinear model, it's a little more realistic in since it will protect a finite but large deflection as I exceed that critical flow velocity. And then with a nonlinear model, I can actually attempt to calculate how big that deflection will be, and I can compare it compare the corresponding stress. Is it large enough to hook up a material or not? That would be a good thing. In practical terms, in a wind tunnel model, often these real wind tunnel models, not the ones we have here because they're on a limited budget, so we have simple models and they're not too expensive. So if you go to one of the NASA facilities, they will have a model in the wind tunnel that costs a few $1 million build in 6 months, and maybe a dozen people contribute in a million ways. And if they break up that model, and they have to rebuild it, that delays the program. That's winning millions of dollars. Or worse yet, the model breaks up and damages the wind tunnel. The wind tunnel will now have to be shut down for 6 months before it can do any testing whatsoever. And they're charging maybe $1,000 a day to test the wind tunnel. So you can do the multiplication. Not a good idea to have a wind tunnel model failure in a major test facility. It's not a good idea to have it fail in the test facility. We had some undergraduates who had a model break up several years ago. And I think it cost about $50,000 to repair the wind tunnel. And probably a few $100,000 a day. So we don't like to do that. Okay. So we can and will analyze this model, but we're going to start with something that's even simpler, which has the essence of the physical phenomenon. And it's a model that's dearly beloved by aeroelasticians. And it's the so-called typical section model. So we're going to draw another line through here and pretend like we're just looking at the cross-section of this line. And so if I look at the cross-section, right, that's the cross-section now. Here's the flow velocity this way still. I'll call it U. And there's this axis about which it wants to pivot, right? And rather rather than model the entire elasticity of the wing, which we could do and will do before the course is over, we're going to think of this wing and its elastic properties, its stiffness properties, its flexibility as being modeled by a spring. And it's going to be a torsional spring because I'm interested in rotation, I'm interested in torsional deformation. By the way, you can build them all like this. What you do is you take a very rigid wing, and then you would put on elastic supports at the bowl of the wind tunnel. We've done that, right? So you can create something that is almost literally this. So now what we want to do is we want to write down an equation of equilibrium, which says that the aerodynamic moments about this point are balanced by the elastic movement created by this torsional spring. Okay. And it turns out when those exactly balance at some critical flow velocity, this system will become statically unstable. So let's see if we can do that. So, we're going to have a moment, which I'll call X and Y. This is the aerodynamic moment. We could have some other moments, but our interest is usually in an aerodynamic moment. And we're going to have an elastic moment, which I'm going to write as K alpha alpha. This is the elastic moment. And alpha is this angle of twist about this point, right? And K alpha is the spring constant associated with the torsional spring. How do I know that spring constant? Well, for the spring, I actually go to the laboratory and apply moments of the amount and see how much it twists. And from that, I infer things about. That's also what you do with a real wind sometimes, right? I may be able to analyze the wind's properties through some mathematical model, or I may just build them and then apply some known mechanical loads and measure the twist from that, infer what the stiffness distribution of them will be. Okay, so that's the structural model. That's pretty easy. What about our aerodynamic model? Well, aerodynamicists are difficult people. Sometimes I pretend to be an aerodynamicist, but then, like now, I'm giving my aerodynamic principle. They're difficult people. Why are they difficult people? Because their notation is one selected as convenient for them, but not convenient for someone. But if you're going to be an aeroelastician, you have to be both a structural engineer and an aerodynamicist. Right? That's why you charge people more money, right? Because you can do both. So the way an aerodynamicist would describe the moment about this axis, I could put EA here if you want to stand for elastic axis. The way they would describe that is not just the moment about that axis. They would describe it in two terms. They would take that as a moment about the AC, otherwise known as the aerodynamic center. And then they would add to that the lift, the total net force perpendicular to this surface or in this direction, right? Times the distance from wherever the aerodynamic center is to the elastic axis, which we will call E. So E is the distance from the AC to the, oh, we should make this cap. EA. Okay. So just for that in a nutshell, let's think of this as a nice uniform plate. It wants to twist about the bed cord. It turns out the aerodynamic center in low speed flow is at the quarter cord, it's at the half floor in supersonic flow, and it's somewhere in between as you go from subsonic to supersonic flow. In fact, one of the difficulties associated with flutter is that the AC moves, this point about which the aerodynamic force will effectively act, moves dramatically as you get to the transonic range, right? It starts out at the quarter cord, eventually it's going to end up in a half void, but in between it can move as a function of approaching the transite condition, as a function of the Mach number. And that proves to be a challenge. Okay. Further than that, we now need to relate these aerodynamic forces in lift and moment. And by the way, at the moment, I'm using the word moment to context. I only need the lift and the moment. Why? Because I'm treating this actually like a rigid body. If I had if this thing bent in the clockwise direction, I would actually need pressure distribution from the aerodynamics. But for this simple case, I only need the lift and the moment. Well, one reason aerodynamicists like the aerodynamic center is by definition, they select that to be the point where the moment about that point, about the aerodynamic center, does not depend on the impact, does not depend on the lift angle. That's why it's an interesting point. Okay? So, this doesn't depend on the lift angle, but the lift does, right? If I change the angle of attack, the lift goes up as I increase the angle of attack. In fact, linear theory says the lift goes in proportion to the angle of attack, right? Well, that's true up to about 10 or 15 degrees, which isn't all that large, right? At 10 or 15 degrees, the flow begins to stall. There's some other interesting thing. It's sort of the onset of profit, actually. But up to, and therefore, airplanes, high-performance airplanes, may actually fly at higher attack, but your ordinary airliner is going at a pretty small angle, right? Because they didn't want to get into this non-linear regime. So we'll pretend like we're in the linear regime. So we're going to write our lift and moment the following way. The lift, as the Wright brothers determined in their wind tunnel test a long time ago, and other people have verified subsequently, the lift goes like the dynamic pressure Q times either if you want to, you can think of this as a two-dimensional with a unit span, or you can think, and therefore I would put chord here, or I could put chord times span. Oops. I've done with that. If L is the span. Okay. And this is the chord. Or sometimes people just write this as S because that's the area, right? So, times a non-dimensional number, which is usually called the lift. So, I'll call it DCL D alpha times alpha. Q is 1/2 the density of the flow, rho, times the flow velocity squared. And it will appear a lot in this course and any aerodynamic course for that matter. DCL D alpha comes from someone solving the equation of fluid mechanics or the shape of the wing and all that good stuff. They come from a computer code, actually, if you're working for Airbus or Boeing. But for low speed flow with L much larger than C, it's known to be 2 pi. It's actually a little less than 2 pi, but ideally it's 2 pi. Okay, so we have L. And then MAC, we're going to write in a similar fashion. We're going to write QS. It's a moment, right? So it needs an extra length, which is usually chosen to be C, times some non-dimensional coefficient. I'll call it C and then C. And by the way, this product of DCL D alpha times alpha is sometimes just called CL. So this is the lift coefficient. This is the lift coefficient slope, right? Because when multiplied by alpha, it gives you the lift coefficient. This one doesn't depend on alpha, so we'll just leave it the way it is. Okay. And where do these forms come from? Well, they come from dimensional analysis. If you think of the Buckingham Pi theorem, they come from basic aerodynamic theory. You can write down the equations and non-dimensionalized and scale limit. All of that suggests this is the right form. And this is the form that's been used for at least 100 years. So I'm not going to change it. This isn't the only form you can choose, but it's a convenient form. So have to be careful. Sometimes people use the half chord rule or chord. Sometimes they do other things. Yes, sir.
What is CMAC?
Well, CMAC is a number. Okay, and it comes out of the theory. If you are an aerodynamicist and you know the aerodynamic theory, or in a wind-tunnel test. In a wind-tunnel test, I would commit this spring very stiff, and then I would have the ability to rotate it to different angles, and I would measure this moment, right? Then I would divide this moment by Q, S, and C, and that would tell me how big this number is. And what I would find is if I change Q, CMAC doesn't change. The moment changes, but CMAC doesn't change. If I change the area, the moment changes, but CMAC doesn't change. Right?
So it's a constant?
Hmm?
It's a constant.
Yes, it's a constant. It's a constant. And if I have a very thin airfoil, very thin, it's 0. So sometimes we're going to set it to 0. If the airfoil is fat enough, or if the airfoil has a shape, you put a straight plate that had a curvature, then this number would not be 0. But for something that's very thin and has very little curvature, then it would be 0. Turns out to be 0, which is nice. Okay, so this is our model. You've got this moment. Now we've drawn on our background of aerodynamics to express it in this form. And now we want to combine the aerodynamic moment, the elastic moment, and write down an equation of equilibrium. The sign convention is the aerodynamic moment is positive goes up, but the spring resists twist, right? So it creates a moment that goes down. So these are of opposite sign, right? So the equation of equilibrium is m sub y minus k alpha times alpha is equal to 0. Okay? So now if we take 1, 2, 3 and put them in 4, we can solve for alpha, right? And see how big it is. How much does this wing twist? Okay. Well, how do we do that? So we have Q, S, C, CMAC. I'm going to do this. I have an ulterior motive. Plus Q, S, ECL, D alpha times E. Right? I'm using equations 2 and 3 now. It's minus K alpha times alpha equals 0. So this is equation 4, but now let me use 1, 2, 3. And now using higher mathematics, I can solve for alpha. Alpha is what? It's QSC CMAC divided by what? K alpha minus QSE ECL CL. Right? Am I okay? Whenever I make a mistake when I'm lecturing, I would say I do that correctly, so I'll stop the question. Did I make a mistake? I'm okay so far. All right. Yeah. Okay. Well, as advertised, if I look at the denominator, this denominator can be 0. I've got a certain K alpha, I've got a certain wing area, I've got E. This number is too high, more or less. If I increase Q enough, then the denominator vanishes and alpha goes to the center. That's divergence. So divergence is alpha tending to infinity when K alpha minus Q S E DCL D alpha equals 0, or solving for Q. Now I'll put a subscript E on it, note I'm talking about a very special Q, namely divergence, is equal to K alpha over SE BCLD alpha. So if I make the string stiff enough, I can make the divergence speed go up. And so often, one of the design criteria for a wing is it's got to be stiff enough that I don't have divergence, right? That would be embarrassing. E is interesting because F is an area, it's a positive number. DCLD alpha is 2 pi, that's also a positive number. But E can be positive or negative. Remember, E, by definition, is the distance from the aerodynamic center back to the elastic axis. So, if E is negative, that means the aerodynamic center is behind the elastic axis. So, if I want another way to prevent divergence is to move the elastic axis forward as a vertical, right? Or better yet, maybe I don't need to move all that way, maybe I just move it up, right? In which case E is 0, right? If E is 0, Q divergence is pretty bad. And so in helicopter blades, if you look at helicopter blades, most helicopter blades have the elastic axis. That's a very traditional design choice. Also, they always have a Nakatopo. Well, I shouldn't say always. Often they have a Nakatopo 12 airplane. So, this simple analysis actually tells you quite a bit. Now, it turns out when I go back and do the wing, I do a wing model. This result is pretty much the same answer, except the wing model tells you how big K alpha really is in terms of the modulus elasticity of the wing, its thickness, its shape, its all those other things. You have to do some more detailed analysis. But the fundamentals of what happens is pretty much this. Okay, that's good. Now, moving right along, let's do a nonlinear analysis. Okay, I mean, that's why I'm saying I'm doing this because just to do linear analysis. Hardly worth my talking about, right? Because you can read chapter 2, and I hope you will. But let's talk about a nonlinear analysis. What do I mean by nonlinear analysis? Well, there are 2 nonlinearities that can take place. One is in the spread, and the other is in the aerodynamics. Remember, I always told you that the aerodynamics, when you get to about 10 or 15 degrees, the linear theory or the aerodynamic lift is no longer the right answer. What happens is the following. Let's talk a little bit about nonlinear modeling. Rather than having K alpha times alpha, I can have K alpha 1 times alpha plus K alpha 3 times alpha Q. Why alpha Q? Well, because if everything is symmetric, then the alpha squared terms don't appear. But I could put alpha squared in mathematically. There's no function. So I could replace K alpha alpha by nonlinear model of my spread, right? Because I could also take DCLD alpha times alpha, which is the linear, without other stuff. This is the linear model of the aerodynamics, right? I could also have DCLD alpha equal 1 times alpha plus DCL times alpha Q times alpha Q. I could also have alpha to the 5th. I could have alpha squared. I mean, it's just think of it as a power series. Okay, I'm just doing a power series or a Taylor series, right? I mean, whatever the shape is, whatever the relationship is between the elastic moment in alpha and the free-end moment in alpha, I can always represent to some degree approximation as a power series. But this would be the simple. In the case of the aerodynamics, well, I'll leave this as a plus sign. This coefficient is negative. The lift actually decreases when alpha goes up, right? On the other hand, most springs, not all springs, but most elastic springs, this coefficient is positive. The spring gets stiffer as the amplitude of deformation of the spring is larger. With aerodynamics, typically, the aerodynamic forces actually go down. But it doesn't matter. We're just going to include this in. So let's go back now and look at our model. So let's go back to 4 and write it as 6. But this is now what's the nonlinearity then? Include. So now what have we got? We've got QSC CMAC. Actually, CMAC now in the nonlinear range might actually become a function of alpha 2. I'm not going to include that. I've got enough trouble with the ones I have. And for our purposes, for illustration purposes, it wouldn't add that much to our discussion. So now we're going to have plus QSE DCL D alpha 1 alpha plus DCL D alpha 3 alpha Q minus K alpha. This has been K alpha 1, that's alpha. K alpha 3 times alpha Q. Okay? Now I'm going to cheat a little bit because I want to do the algebras as easily as possible. I already know what happens in the linear model. What happens in the linear model? Divergence occurs. That's what I'm really interested in, divergence. Okay? And it occurs when the non-linear vanishes. Divergence doesn't really depend on what the numerator is. It's just there. So I'm now going to set CMAC 0. Because it is really close to 0. Interesting here, right? So I'm going to eliminate that term, just because, mainly because it's convenient mathematics. And it turns out I still have enough left in my model that I can say some interesting things about the physical phenomena. Okay. So now, keeping that in mind, this is what the mathematicians call a homogeneous equation, right? All terms involve or a power about. Now, one possible solution is alpha equals 0. That's true. That's okay. But that's not the interesting solution. The interesting solution is alpha isn't 0. Okay.
I'm not sure.
I'm going to cancel out the factor alpha, so alpha cubes will become alpha squared, and the alpha terms go away. Right? And now I'll collect terms. This is what I got. I've got QSE DCLD alpha 1 minus K alpha 1. Those are the terms that involve just alpha. And then I've got plus QSE DCLD alpha Q minus K alpha. Not Q, but 3 times alpha squared, right? Equals 0.
Okay. Watch this.
Okay. Well, what does the equation tell me?
It's really hard.
Let me just to give you the picture. Let me first of all consider the case where the aerodynamic nonlinearity is not there. Right? I'll come back to that in a moment. But that's true. Then I have QSE DCLD alpha. That's K alpha 1. Minus K alpha 3 alpha squared equals 0. Or put it on the other side, as I want to do. Unless and this is a positive number, right? It's greater than 0.
Yeah. Right.
What is this?
You should ask him.
Am I extension. Stockholm trying to tell me something? Stockholm, do you have a question?
Yeah, tell him that it's stuck.
The video is nice enough.
Oh. Well, just as I came to the good part.
You're first. Go ahead and close and rejoin us. It looks like you're moving now. Can you see us moving?
Yeah, we can see you, but the notes are part of the note is green. You can see your video.
That's it?
Yeah, that's it.
Okay.
Yeah, we see the problem. We're working on it. This is an excellent time for questions for Dr. Dowell. That's true. Dr. Dowell, can you repeat where you were doing the CL, it's just in your mind right now.
Why I'm throwing it away?
Yeah.
Oh, of course, it's going to make my discussion easier. I'm going to put it back. And it's not a permanent discard. It's only a temporary discard to make a point I want to make.
All right, Stockholm.
No worries, means that we can see you, but the part of the note will display that is black.
Okay. So you cannot see the page 4 that's on the table right now?
Yeah, on the table we can see you.
Okay, let me see. I have a question. Like, when you're making the non-linear model, why do you make it like alpha and alpha 3 times y out alpha plus alpha squared?
Yeah, the answer is really for convenience. Physically, it would be interesting. It would be only alpha, only the odd powers of alpha. One has a symmetrical pair.
You can see?
Okay, but not symmetrical, so the top and bottom are the same. Then it turns out the opposite here. The symmetry in that instance. Okay. But in general, you could have apple square terms as well. And that wouldn't really fundamentally complicate what we're saying. It would make the algorithm essentially the same. Okay. Stockholm, are you now with us? Can you see my paper?
Yes. Yes.
Okay. Now, how far back would you like me to go? I was talking about the non-linear. Had you stayed with me until we did the linear divergence calculation and reached equation 5?
This is the last part. You will get the
Okay. So I was now generalizing our mathematical model to the nonlinear case, and to do that, I was taking the linear spring representation and now making it a nonlinear spring with an alpha cube curve, alpha squared, and I was taking the linear aerodynamic model and again generalizing it to the nonlinear case and then between an alpha cube term. But I did note that alpha the alpha to the third power, that coefficient typically is a negative number, while this coefficient is typically a positive number. Okay? Are you with me? All right, fine. And putting all of that back in, we could into the equation of equilibrium and eliminating this for convenience without any essential loss of information. We can solve this equation. And then I got to here. And then I said, by the way, we're going to let this term be throw it away. But if you don't want to throw it away, I'll leap ahead a little bit. Remember, this term is negative. That means this entire coefficient is negative. And that means when I put this term on the right-hand side, entire coefficient to due to both the aerodynamic and the structural nonlinearity will be positive. So now I have an equation like this, which will allow me to determine alpha squared. This is a positive number. Even with the nonlinear aerodynamic term, this coefficient will still be positive. So now I have alpha squared times the positive number is equal to this thing. What about the left-hand side? The left-hand side will be negative if Q is too small, right? Because of this sign. That means if I'm below the divergence condition, the left-hand side is negative. Alpha squared cannot be a negative number physically. What that really tells you is alpha is 0. Right, if I'm below the divergence condition. Conversely, if I'm above the divergence condition, this entire coefficient becomes positive. This is positive, I can solve for alpha squared. And alpha squared is physically realizable. And by the way, it's alpha squared, not alpha. So the solution for alpha is plus or minus. Right? It's plus or minus the square root of this thing. So if I plot alpha versus Q, and now I'm going to normalize it by Q divergence. That Q divergence is what I got from linear analysis. And here's one. That's when I'm at the divergence condition for linear analysis. Up to this point, for all values of Q, the solution is 0, provided I have set C and AC equal to 0, right? Beyond that point, the solution looks like this. It's symmetric, right? And this is the plus branch, if you will. And this is the negative branch. Okay? This branch actually still exists, but it's unstable. If you go back to the original question, remember I said alpha equals 0 is always the solution? Well, it is. It's always the solution even beyond divergence, but it's an unstable solution. I haven't proved that's unstable. I'm asking you to accept my word as a scholar and show me that's unstable. Later on, we'll see how we can demonstrate that it's unstable. But at this point, we're just going to do that. Okay. Now, solution, I'll draw this as a solid line. These solutions are strictly speaking for the case CMAC equals 0. Okay? Now, in the next 5 minutes, we'll pass our class concludes. What do you think the solution would look like? I'll draw it as a dash line. If CMAC were not 0. Well, if CMAC is not 0, there's going to be some twist, even a small q. And whether the twist will be positive or negative in small q will depend on the sign, positive or negative of CMAC. Right? So what will happen then is, strictly speaking, if q equals 0, of course, there's no aerodynamic force at all. So it starts out at 0, but then it'll go like this. It'll be something non-zero. It's still going to be pretty small. And then when I get close to the divergence, it'll do that. Okay. Well, there's another branch. There's another branch which I think, as I recall, comes in from infinity. And goes like this. Okay? So there are two branches of the solution when CMAC is 0. There are also two branches when it's not 0. But the two branches when it's not 0 are a little more complicated. That's why I didn't want to talk about that first. Okay. Now, remember, when CMAC is 0, this branch is unstable. What do you think it says about this branch? I claim a part of this branch is unstable and a part of it is stable. Which part is stable and which part is unstable? Well, here's the nose. This part of the branch is actually stable. This part of the branch is unstable. This branch is always stable. What do I mean by stability in this case? Well, stability can't be a delicate issue. What I mean in this case is if I give this system a gentle nudge, a small perturbation, then the solution will go back to one or the other of these stable branches. And whether I'm on this branch or this stable branch depends on how I start the solution. If I change the size, you may see that will reverse this, right? Also, in principle, if I were on this branch and gave the system just a big enough kick, I have to be very careful about how I kick. I could actually kick it from this stable branch to this stable branch. But I could never physically, or even mathematically if I'm doing the numerical analysis, I could never actually get to the unstable branch because the slightest perturbation always takes me away from an unstable branch. You know, this is an interesting case. Unfortunately, I don't have time to go into detail. So our general procedure in this course is when I don't have enough time to do something interesting, I assign as a homework. Right? So what I will do is I'll work out some numbers, and we'll let you work out the case when CMAK is not 0. And that'll be fun, right? Okay. What other questions might you have? No questions from Durham? Stockholm. I'm sorry for the glitch. I hope we still got the essence of what we were discussing. Any questions before we conclude for the day? Yes, sir. Yeah. No, they still look similar. I think what will happen is, see, there are two branches with the alpha cube term. I think it will depend on the sign of the coefficient in the alpha 5 terms, but you'll get a different branch. Additional branches, possibly, depending on the sign of the coefficient. Let's just look at stiffness. Forget about the aerodynamics for a moment. You added a fifth term and all the coefficients of alpha cubed, alpha 5 for the spring stiffness coefficients. If they were all positive, I think you just get them. I mean, change the shape a little bit. I don't think you'd get additional branches. But therefore, if I change the sign of the spring, where the stiffness curve is sign, alpha 5 might be negative, alpha 2 might be positive, and vice versa. Then I think you could certainly get additional complexity and probably additional branches.
So, you mean the number of branches is not determined by the power? It's determined by power.
Yeah, well, think of it. Principally, this equation of equilibrium is just a polynomial in alpha, right?
Yeah.
If I have a fifth-degree polynomial, I in principle have more solutions than if I have a third-degree polynomial, right? So whether those branches will be stable or unstable, it depends on the size of the coefficient. But yeah, if you added additional power, you could get additional solutions.
So, one question?
Just pass it in, so I'll be right with you. Yes.
Can you repeat why you say that K alpha is positive because of stiffness?
Yeah. I'm just saying for a typical physical spring, K alpha 3 would be positive.
K alpha 1 is positive.
And K alpha 1 is also positive. So for real physical springs, those coefficients for the non-linear stiffness are typically positive. Whereas for the aerodynamic coefficient, the non-linearity in the aerodynamics is such that the lift comes down. Therefore, C alpha 3 is typically a negative number if you use this model. Stockholm, yes, you have a question?
I am why you don't know that 0.
Yeah, could you say that?
Say a little more clearly?
Yeah, could you get closer to a microphone so I can hear you?
Yeah, I miss why DCL the alpha 3 goes to 0.
Why is the alpha to 0?
Why?
DCL the alpha goes to 0, I think is the question.
Well, that's the question. I mean, I understand why you, if that's the question, I understand the question, but I understand why you would say.
DCL the alpha 1. Going to 0.
DCL the alpha 1 is not 0. It's simply an undefined.
I mean DCL the alpha 3.
That. I just momentarily deleted that term to concentrate on the structural stiffness nonlinearity to make my discussion simpler. But then I pointed out to you that DCL the alpha 3, if I included it, is normally a negative number. Therefore, this entire coefficient is a negative number. But then when I place it on the right-hand side, so I can solve for alpha squared, that entire coefficient would be a positive number, and therefore, this is still qualitatively the picture you have, even when you include the aerodynamic nonlinearity. Does that help?
Yes, yeah.
Okay, thank you.
Thank you.
Other questions? Okay. I know you're going to be working hard on the homework tonight, but what else are you going to be doing tonight? Are you going to be at the game? Oh, really? Well, I'm counting on you cheering louder than you cheered the last couple of games, because you really let it down the last two games. I don't want to blame just you. I know it wasn't Charlie here. So, okay. Great. We'll see you again on Thursday.
Control surface is kind of a bucket. I